All right. So, good evening and welcome back to the weekly live sessions on wheel mobile robots. So, my name is Isaac John. I am a PhD scholar from IIT Palakkad. And yeah, so I hope the courses went so well so far. So here we are actually, right at the end of all the courses, So, yeah, let's have a very brief overview of all the topics that we have covered so far. So, like basically, our course had a. I would like to see our course which had three sections, right? So, week one, I would classify week one, week two, and week three under you could probably classify them as under the topic mechanics of wheel mobile robots, right? Because here we actually considered the developing the mathematical models of various wheel mobile robots. We dealt with various key definitions such as degree of mobility, degree of freedom, degree of maneuverability. All those key definitions we covered in week one. And on week two, we saw how to derive the kinematic model, and we have already discussed the mathematical aspects and some questions in the course. But if you have seen the videos, I think the professor have also shared, how to simulate, how to perform the kinematic simulation of wheel mobile robots through MATLAB. So you could actually you could actually consider them to be an implementation of what we have learned in the course. And on week three, we have considered the dynamics, how to derive the dynamic models or the governing equations of motion of a wheel mobile robot. So like these encapsulate the real physics behind the motion of a wheel mobile robot. For example, if some forces are acting on the wheel mobile robots, and if you're supplying some torque to the wheels, how would the mobile robot would react in real time? So there also in the lectures we have seen the simulation of dynamic models using MATLAB. Very rigorous approach was shared in the course. And for the remaining 3 weeks, for the subsequent 3 weeks, week four, week five, and week six, here we basically considered the topics related to sensing, or I would rather call it as perception, which we where we discuss the various sensors and actuators used in a mobile robot for its motion as well as its for its perception of the environment. And on week 5, we have actually covered the topics on localization. And the main essence was, developing some mathematical models to, essentially identify or locate the position of the mobile robot provided a map was given. So not only a map, not only we rely on the map data, we also rely on sensor data. And we actually discussed two algorithms, the Markov localization as well as Kalman filter localization, which essentially gives a brief overview of how to fuse, the data from odometry, or the predicted data as well as the data from the sensors, how to fuse these data to have a very good estimate of, where the position of the mobile robot is. And on week 6, we have seen navigation algorithms. So this part essentially consisted of graph construction, and graph search, where in graph construction, if the mobile robot has localized itself, it should be aware of its start position and end position. So in graph construction, we would be constructing several road maps, connecting connecting the start position all the way to the end position, and using some of the graph search approaches. Whatever we have discussed on week 6, we will be able to select the most optimal path, out of all the multiple roads possible. And on week 7, we discussed on motion controllers, the basic design of motion controllers. This is actually very relevant in real time control of a mobile robot, because in the introductory lecture of week 6 itself, it was made clear that whatever we model mathematically, whatever we model using the dynamic models, it is never going to be a real representation of a mobile robot, because there could be a lot of unmodeled physics in the dynamics, and several parameters may not be estimated correctly. So, the motion predicted by the dynamic model could be a bit different than, our actual desired motion or actual desired trajectory. So we would use some sensor data, we would use some feedback so that, the trajectory of the mobile robot can be adjusted. So for that, we need to design motion controllers, and, we have essentially done that in week 6. And we have discussed various topics regarding, open loop controls. And we have also seen closed loop controls. And within this open loop controls, we have seen the kinematic and dynamic models or dynamic controls, which are open loop. And within the closed loop, we have again seen, the kinematic control as well as the dynamic control. And again, if you were following the lectures, the simulation of, how a motion controller works was also depicted by using MATLABs. Sorry, that was actually for week 7. And for week 8, for today's session, it's just like an outro, to the course. Just like how we started our course based on a general by giving a general overview of all sorts of mobile robots. We would also we would also we would have an outro based on the similar topics. We would basically cover other forms of mobile robots, not just wheel mobile robots, but other modes of locomotion, and their defining characteristics. So Having said that, let's have a brief overview of all the topics that we have covered in this week. So this is everything. Most of the things that we are covering for this week are mostly descriptive. So I hope it would be all right if I just glance over the topics, because these are all self-explanatory, and there is not much to be discussed about all these things. So the first topic for this week for multiple mobile robotic systems, which essentially facilitates cooperation between multiple robotic systems. So we could have multiple mobile robots in an environment, and each of these multiple mobile robots within the system should have to coordinate to realize some tasks. So, what are the common motivations for developing a system that has multiple robots? So, the task complexity is too high for a single robot to accomplish. It's a pretty straightforward point, to understand, because one example I could give is that, like, in very complex machining processes, like if you want to machine a very complex part with very intricate geometries, you could either design a very complex robot which has all 6 degrees of freedom, or you could have a different approach where you could have a planar workpiece bed, which can move in all three directions, x, y, z translations, and you can have a machining head, which can rotate in three directions. So, like, by splitting all the 3 degrees of freedom, three for the machine head and three for the tool bed, you can in effect you can basically have two simpler robotic systems rather than having one complex robotic system. And in a lot of applications, having simpler multiple simpler robotic systems could prove to be beneficial, than having a single complex robotic system. Because if the robotic system is complex, its control could be very difficult in real time, and the cost associated with fabrication development, would shoot up exponentially as the complexity increases. So that is the prime motivation for having a multi-robotic system, when when the choice is to either have a simpler multi-robot system or to have a complex single robot system. And another aspect would be, if we can employ a multi-robot system if the task is inherently distributed. So, a simple thing is that, like, if you have a very large object, you can easily, lift up this payload by, delegating it to multiple robots, at crucial points. So, like, these sort of things, asking for a cooperation of multiple robots uh, for picking up a payload or picking up an object, these sort of things can be easily distributed. Another the third part is, building several resource-bound robots is much easier than having a single powerful robot. So that is also essentially what we have discussed in point one. Having building or delegating the task to multiple simpler robots is inherently much more easier than having a complex single robot. And in point four, multiple robots can solve problems faster using parallelism. So the keyword to notice is parallelism, right? So in parallelism, the order of executing a task is not uh, would not make any difference. So, for example, if you have you know three or probably five objects here, and your goal is to pick all these objects and simply place it on a bin at a different location. These sort of tasks are easily parallelizable, right? So in this sort of case, you can deploy probably multiple robots, And simultaneously, you can actually ask, each of these robots to, pick up one obstacle and then, you know, deliver it to the bin, right? So the order at which they do so is not very important. So these sort of tasks can be easily parallelizable. But, if the order of placing the obstacles or the objects into the bin is of concern, then such tasks cannot be serialized, right? So such tasks cannot be parallelized. So the keyword is actually parallelism, where you can easily deploy multiple robots when the tasks are inherently parallelizable. And for the fifth point, it says the introduction of multiple robots increases the robustness through redundancy. So, this is very similar to what we have discussed on, week 4, where, in a GPS system, we have multiple redundant satellites, right? So if one of the satellites failed, the backup satellites can, take the place of the failed satellite. So, the robustness is actually pretty much taken care of by redundancy. So, similarly, in the case of a multiple robot, so if a few of them dies off, the entire task would not be affected much, because there will be additional robots, redundant robots, waiting to be, you know, uh, waiting for to make the substitution. So the robustness due to redundancy is actually a very key factor for considering multiple mobile robotic systems. And then you can have a very involved classification of multi-robot systems. So the major classification is, you can classify it as a collective swarm system, or the other part could be intentionally cooperative systems. So in collective swarm system, the most important highlight or the most important feature of a collective swarm system is that all the robots in the system are homogeneous, right? So each and every robot within this collective swarm system, they are exactly identical in every sense. Like they have the same, sensor capabilities, they have the same actuator capabilities. So, just like how, how they are called, they're called collective swarm systems. And if we call swarms as a collective noun for, probably if you want to call a group of insects, or, group of bees, or a group of mosquitoes, insects, we collectively define, or we collectively address them as swarms. And, the defining feature is that each and every part, or each and every organism within the swarm is the same. If you are referring to a swarm of bees, everything would be a bee. Or if you're referring to a swarm of wasps, they are indeed wasps. So the defining feature is that, they are homogeneous, which essentially means that they are basically made of identical robotic systems. And here and another feature is that, like, in a swarm robotic systems, each individual each individual member, need not be aware of what the other members are doing, right? So, for example, if the task for a swarm system is to lift a payload, by equally applying some forces uniformly through multiple points. So you could probably consider all these black uh, circles as drones, drones in a swarm system. And if it is required to lift this payload, you are only required to program each and every member of the swarm to where it has to position itself, where it has to position itself with reference to this payload. And we don't really require, or each of these individual systems is not really required to know what the other systems are doing. So, the communication between other systems or other members are not much of a concern, because each and every robotic systems will be fully, given instructions uh, ba based on which they are required to perform some task. Whereas in the case of this intentionally cooperative systems, some amount of information has to be shared among the members of a multi-robotic system. So depending on how much information is being shared or how much independence each of the system has, they can be again further classified into weakly cooperative systems, depending on their level of cooperation. Or in the other case, you can call them as a strongly cooperative systems. And here in intentionally cooperative systems, the member robots can be homogeneous or non-homogeneous. But in Swarm, it's exclusively for homogeneous. Each members are exclusively homogeneous robots. And let's have a brief overview regarding the different classifications. So in collective swarm systems, robot executes their own task with only minimal need for knowledge about other robotic team members. So as we have said, they only require minimal knowledge about what other members are doing. And these systems are typified by the assumption of a large number of mobile robots. So just like how we observe a swarm, they consist of a very large number of bees or a very large number of insects. So in a typical fashion, a swarm systems typically consist of a large number of mobile robots in which robots make use of local control laws to generate a globally coherent team behavior with little explicit communication among others. Right? So, the control laws are local to each of the robotic systems. They don't really have to communicate among each other. And each of these local control laws will be will be uploaded by a centralized server or a centralized robot into the swarm robots. And moving on to this intentionally cooperative systems, they have knowledge of the presence of other robots in the environment and act together based on the state, action, or capabilities of their teammates in order to accomplish the same goal. So each and every robot is actually aware of the capability of various members within its own system. So if a collective task is to is to maybe pick an object and place it somewhere else, for that to happen, it's actually the robots will have to collaborate based on their capabilities, their mechanical architecture, their sensors, actuators, all such things. And so the robots within that environment, they have to make a decision based on which of the robotic system has an appropriate actuator for picking up an obstacle. And so one robot could be picking up the obstacle. Some other robot could be observing the environment for the other robot. You could also think it in another way. If the robot picking up that obstacle is blind, it cannot perceive its environment. It can only pick up and drop it, right? So in that case, maybe some other robot which has which has some vision sensors or which has some other sensors to sense the position of the ball and where to drop it. These two robots can actually coordinate. So it's like guiding a blind person. Someone who has eyes, he can actually uh, guide a blind person to cross the road because he's essentially blind, but he has the necessary capabilities for locomotion. So a similar approach can be thought about for intentionally cooperative systems, because not every robot has all the capabilities. Some robot, some members have, much more advanced perception capabilities or sensor capabilities, and some other robots have better actuators for a task. So it requires a cooperation of all these sort of multiple systems to execute execute a particular task. And the second point is they vary in the extent to which robot take into account the actions or state of other robots and can lead to either strongly or weakly cooperative systems. So this essentially leads us to the two more sub classifications. Depending on how much they are cooperating, you could either classify them as strongly cooperative or weakly cooperative solutions. So let's have a brief overview of what these are. So like it's as the name suggests, in a strongly cooperative systems, it requires robot to act in concert to achieve the goal, executing tasks that are not trivially serializable. So essentially, what we have discussed in the previous slide, the member robots will have to act in concert, or will have to be synchronized so that a task can be executed. And the second point is they require some type of communication and synchronization among the robots. So each member will have to react based on what other members are doing. So that's what the synchronization means, and synchronization essentially require uh, very very frequent communication as well. Uh, and whereas in weakly cooperative solutions, they allow the robots to have periods of operational independence subsequent to coordinating their selection of tasks or roles. So, weakly cooperative solutions, like they may not be cooperating at each and every point of time. Like they only need to be cooperative when the situation arises. And for any other applications, they'll be doing their own designated tasks. And in case if a single robot cannot be able to perform a specific task, and it may require the help of some other member, at that point of time they may have to cooperate. Apart from that, in most of the cases, the members will operate independently. And in case two, they can deal with heterogeneity. So this is a very important factor uh, in the robot team members, in which members can vary their sensors and actuator capabilities. So heterogeneity means each members can be, and then each members of a weakly cooperative system can be completely different. Based on their mechanical architecture, based on their sensing and actuator capabilities. It can be the members can be completely entirely different robotic systems. And point three essentially says the coordination of robots can be very different from the collective swarm approaches, since the robots are no longer interchangeable. So just like what we have discussed 2 slides ago, in case in ca- in, ca- in the case of a collective swarm approach, if one robot fails, another robot can easily take place of the failed robot, because they are all homogeneous, right? But in case of a weakly cooperative systems, because of their heterogeneity, if one robot fails, some other robot within that system cannot make a substitution for that failed robot, because the robots are entirely different, or uh, they are completely different. So a substitution cannot be made as easy as in the case of a collective swarm approach. And now, once we have discussed what are the different kinds of multi-robotic systems, now we basically see some control architecture of a multi-robotic system, right? So control architecture essentially means how the flow of controller occurs in a system that has multiple robotic systems. So like if we have a system with multiple robotic systems, one, two, three, four. how does the flow of control happen? Maybe between a central server and among each of these robots. So that is what we discussed in in the control architecture, and there are four different philosophies uh, that are commonly employed, which are named as centralized control, hierarchical control, decentralized control, and hybrid control. So let's have a brief overview about their uh, definitions. So these are again not very complicated. These are essentially very straightforward. Once you have gone through the definitions. So in the centralized approach, it coordinates the entire team from a single. Uh, there's a term missing actually. Maybe a single. Maybe I'll name it as a single server, or probably or a vantage point. Right. So let's go back to the definition. Uh, so in a centralized system, it coordinates the entire system from a single server or a single vantage point, although often practically unrealistic due to their vulnerability to a single point of failure, and due to the difficulty of communicating the entire system state back to the central location. I think it's a long statement, but essentially what it does is that there will be a central server, right, which monitors the action of all the constituent members of a multi-robot system. So if I call this as server, and if you have a multi-robot system, maybe I'll label them as 1, 2, 3, there will be a direct flow of communication from the server to the member robots. And the communication among the the member robots, that could depend whether or not they are weakly cooperative systems, strongly cooperative systems, or collective swarm systems. But in case of a centralized system, each of these robots, there will always be a direct line of communication from the server to the constituent robots. And the drawback is that there is a very significant vulnerability, because if the server fails, then the entire robotic system fails, right? Because there won't be any flow of control between the server to the other systems. And if one of the robot also fails, if the consistent robot also fails, then this could also affect the task where this multi-robot system is actually employed, right? Because we require all three robots, and if one of the robot fails, then the task is also compromised. So in case of a in case of a centralized system, it's actually very vulnerable to a single point failure. And the second point says the situation in which these approaches are relevant are cases in which the centralized controller has a clear vantage point from which to observe the robots and can easily broadcast group messages for all the robots to obey. So, like, this is suitable for a situation where it is easy for a server to observe all the robots within that multi-robot system, and it's also easy for this server robot to have a broadcast message, like when all the robot is within the vicinity of that server, the communication can be maintained. But the drawback is these are susceptible for a single point failure. And the second definition is hierarchical architecture. So in this control approach, each robot oversees the action of a relatively small group of other robots, each of which in turn oversees yet another group of robots, and so on and so forth. Right. So here in this case, we have, one robot at the top level. Maybe I'll, depict this as level one. And the task at level one can be delegated to multiple robots at level two. Maybe I'll denote all the robots on level two as number twos. And then they would delegate their tasks further down the line to level threes, so on and so forth. Right? So the tasks would be delegated down the levels. Uh, yeah, and moving on to the second point, this says the architecture scales much better than centralized approach, and it is reminiscent of a military command and control. So, like this is how military, it's very similar to how officers or officials are ranked in a military flow of control. At the bottom we have soldiers, and going up we have lieutenants, and probably at the top we may have captains, marshals, and all those officials higher up the level. And the key feature, or the key characteristic of this architecture is that a point of weakness for hierarchical control architecture is recovering from failures of the robot high in the control tree. So, like if there is a failure at a higher level, then every other subsequent levels would be inoperable, right? They would go out of operation. But if something fails at the very bottom level, these can be easily replaced, right? Because as you can see, as you go down the levels, there are more number of similar kinds of robots, right? So like we have only a single level one robot in this example, and we have three level two robots, and we have six level three robots. So if something fails in level three, it could be easy to, it would be cheap to replace, the robot at the lower levels, or maybe you can probably redistribute the task among the remaining functional robots. These are not much of a concern. But if something fails higher up the level, if level one or level two fails, then all the other flow of control, below that failed robot would be affected, and that could probably render the entire system to be inoperable. So yeah, that is about hierarchical architecture. Then we have something called the decentralized architecture. So the first point is it is the most common approach for multi-robot systems, and typically require to take actions based only on the knowledge local to this situation. So in this case, we have a multiple robot system, and this is not really required to communicate, with the central server. Like each robot, the tasks for each robot would be clearly specified for each of these robots. It is not really necessary to delegate the task from a central server, right? Each of the robots are programmed to do a specific task, and it's not really required to have some sort of communication among each other, right? So they take actions based only on the knowledge local to their situation. This control approach can be highly robust to failure, since no robot is responsible for the control of any other robot. So, like, unlike the hierarchical architecture, like if a robot at the higher levels fails, everything down the line will also be inoperable. But in case of a decentralized architecture, if one robot fails, since it is not really affecting any other robot, the operations of all the remaining robots are not really affected. You can simply replace the failed robot by an exactly identical robot, and the tasks can be resumed. And this entire thing will not affect the other functioning robots. And the third point is achieving global coherency in these systems can be difficult because high level goals have to be incorporated into the local control of each robot. So the problem is that like every time you want to change the task, or every time if you want to replace a robot with an identical robot due to failure, you have to program each and every robot accordingly, right? Like for example, if all the four robots were doing a particular task, and once that task has been finished, each and every robot will have to be reprogrammed for the new task. So that becomes a bit cumbersome uh, in the longer run, right? When for every other task, you have to program each and every robots to a very high level. But that wouldn't be a case in case of a centralized control, where you can simply delegate the controls from a central server system. But here you have to program each and every robot depending on the task. Fourth point says, if the goal changes, if the goals change, it may be difficult to revise the behavior of individual robots. So, this just reinforces what we have said earlier. If the goal changes, or if we want the robot to perform a new task, every time we have to reprogram it, and it could it could prove to be difficult. And lastly, we look at this hybrid control, or this hybrid architecture. It combines the local control with higher level control approaches to achieve both robustness and ability to influence the entire team actions through a global goals, plans, and control. So this essentially combines the advantages of a centralized control, where you can actually use a centralized server to, influence or program, the entire actions, or, the entire actions of all the constituent members. And at the same time, you can also, supplement the members with a higher level local control as well. So in case if one robot fails, other robot can still continue the task. And if you want to, if you want to reprogram the system for a new task, you can do that through a central server. The problem two statements two states many multiple robot control approaches make use of hybrid architecture. So like it's very widely used, for their robustness, as well as the ease with which the system can be recalibrated to a new tasks. So yeah, that was about the various architectures we discussed in multi-robot system. And next, we would be discussing very briefly about autonomous mobile robots and automated guided vehicles. So, like these are, although the names is most likely to convey the same meaning, there are a few subtle differences. By the by the purposes of which we would employ an AMR and an AGV. So, in case of an autonomous mobile robot, or an AMR in short, mobile robots can be AMRs, which means they are capable of navigating in an uncontrolled environment without the need of a physical or electromechanical guidance devices. So, they are fully autonomous. They can make their own decisions. They can also work in an uncontrolled environment. So like whatever we have studied in this course, it has provided us tools to fully design an autonomous mobile robot, right? It can predict its next position using the mathematical models, and it can verify whether the predictions are true or not, using the sensors, and to execute to execute its motion from its start position to the goal position. It can use the strategies we have discussed in localization, as well as motion controls. So like everything is autonomous, decision making is done automatically. Whereas in the case of an automated guided vehicles, or in case of an AGV, mobile robots can rely on guidance devices that allow them to travel in a predefined navigation route in a relatively controlled space. So AGVs are used in a controlled space, for example, in warehouses, and the path through which they move are also predefined, right? Maybe they can probably move through rails, or they can be made as a line following robot. Like for example, if your warehouse floor has some sort of a marker, maybe a black marker or some sort of a marker that can be detected through uh, some sensors, maybe some vision sensors. The robot would only follow these paths. So it does not really have to decide on which path to take. It does not really have to implement any sort of a navigation algorithm. It is only required to follow the path. Uh, uh, that too in a very relatively controlled space. I mean, it still requires some sort of a navigation algorithm, because in order to reach this final goal position, there still could be multiple paths, and it can take a decision based on which path is shortest. But again, it's a much more easy process than how an an AMR would do, right? Because it has to do this graph construction method. It has to uh, keep on updating its surroundings, and at the same time it also has to do a graph search to identify the optimal path. But in case of an AGV, the paths are all preloaded into it, and it only need to find out the shortest path to get to that goal position. And they are also used in the control space, like for example in Amazon warehouses, or warehouses of online shopping, uh, 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 you know, shopping platforms. The items would be arranged in their respective shelves in a warehouse, and if a command is given to the robot, or to a system of robots to retrieve a particular object from the warehouse, the robot can easily go to that particular shelf, and it can easily retrieve that object, and it can easily deliver it back to the packaging station. So that is where we employ these AGVs. Their task is relatively simpler compared to this AMRs. And the key differences between AGVs and AMRs are, in case of AGVs, they have fixed routes. Their routes are actually fixed using some markers. They cannot deviate from that fixed route. Whereas in case of AMR, they actually determine their own paths, using the graph construction and graph search methods. They determine how to reach from the current position to the goal position. And in case of an AGVs, they have limited applications, right? Because since their paths are fixed, their flexibility is much lesser compared to an autonomous mobile robot, right? Based on the task, it can be easily programmed, and it's also much more flexible in that it can make its own decision. It does not have to follow any predefined path, uh, and a lot of things it does. Yeah, it does a lot of decision making in executing in a lot of things. So in that regard, AMRs have high flexibility, and in case of AGVs, they are suited for traditional business models, where you are only required to bring only a small level of automation in a traditional business. But if you want an agile business, which keeps on changing its tasks, or which keeps on changing its goals, you need an intelligent robotic system such as an AMR, which can do a lot of decision making. And AGVs are expensive because every time you have to change your task, or every time you have to have some sort of flexibility, you have to completely reconfigure, or you may have to deploy a completely different system. But in case of an AMRs, they can be easily reprogrammed. Nothing has to be changed. Only a small recalibration is required in case of an AMR. So that was about the key differences between AGVs and AMRs. And moving on to some more other definitions, we would also like to see what a mobile manipulator means, right? So essentially, at the very beginning of this course, we have seen a very broad classification of robotic devices based on whether or not they are manipulators, or whether or not they are locomotive devices, such as a mobile robot. So you can classify a robotic system based on their effect on the environment. Either it could be a manipulator or it could be a mobile robot. But in case of a mobile manipulator, you combine the features of a manipulator as well as a mobile robot. So here on the left hand side, this is a typical example where you have a mobile robot base with 4 wheels. This is a wheel mobile robot, and on top of this wheel mobile robot, you have a robotic manipulator. So like this has the features of both a wheel mobile robot as well as a robotic manipulator combined together. Because as you would know, a manipulator on its own has a very limited workspace, right? Because its ground is always fixed. But if you mount a manipulator on top of a mobile robot, its workspace is practically unconstrained, right? Because the mobile robot can move wherever it wants, and as a result, by extension, the manipulator will also have a you know unconstrained workspace. So this is another example where a manipulator is mounted on an underwater robot. So here, this is basically an example of an underwater robot, and the way by which underwater robot moves is using these thrusters, mounted at different directions. So here, probably you may have 8 thrusters, two of them facing vertically upward, and four of them, facing in a direction orthogonal to this vertical direction. So that depending on how much thrust each of these thrusters make, the mobile robot can actually execute 6 degrees of freedom. It will have 6 degrees of freedom. And using a very similar principle, you have the third example where a robotic arm or a robotic manipulator is mounted on an aerial drone. So in place of these thrusters, you have these rotors, which would provide the necessary thrust for the aerial robot to move in all 6 degrees of freedom. So the key definition of a mobile manipulator is that a mobile manipulator is a robot system built from a robotic manipulator arm mounted on a mobile platform. So mobile platform could be a wheel mobile robot, it could be an underwater robot, or it could be an aerial drone. Such systems combines the advantage of mobile platforms and robotic manipulator arms while reducing their drawbacks. So a drawback of mobile robot is that, like, on their own, they cannot do any manipulation task. They simply move about, but they cannot manipulate any objects. And the drawback of a manipulator arm is that they have very limited workspace. But if you combine them together, that drawbacks will not be a matter of concern. For instance, mobile robot extends the workspace of an arm, right? So mobile robot practically makes the workspace of an arm unconstrained, whereas an arm offers several operational functionalities. So, the features of the robotic arm and the mobile robot complements each other. All right. So that is about mobile manipulator. Let's see, some more features of a mobile manipulator system or a vehicle manipulator system. So a vehicle manipulator is a robot that is intended to operate with the dexterity in a workspace larger than that of a fixed base manipulator and consists of two main parts. So like just like what we have said, dexterity means, if a robot is capable of reaching a point with all possible orientations, we call that point to be a dexterous point, right? Like one example is that like if we fully stretch our arm, that extreme point, where we can reach by our finger, we can only reach that point by a single orientation. But any other point, that is close to our body, we can reach that point with any arbitrary orientation. So this dexterity basically means, you can reach a point with all sort of orientation, and a vehicle manipulator essentially uh, you know, uh, imparts now an unconstrained dexterous workspace. And the main parts are a base, normally with actuation, which can move freely with an environment, one or more manipulator arms on the base. So vehicle manipulator will have a base. The base can move around in the environment. It can be a wheeled base. It can be an underwater base. It can be an aerial base. Anyways, any sort of locomotion system, and the base will be mounted by one or more manipulator arms. It is not really relevant to have a single manipulator arm. You can probably have more than one manipulator arms. And the second point is the base is what gives the vehicle manipulator system its stability to locomote over what is often a large geographical area. So, typically an arm is constrained within its workspace, but a base would essentially make its workspace unbounded or unconstrained. And point three basically says the base can be a vehicle in a normal sense, such as a car or a satellite or an underwater vehicle, or it can be a robotic device that allows for motion uh, in a more restricted area, such as a rail, gantry, crane, or a steward platform. Again, these are all very self-explanatory. So a vehicle manipulator essentially consists of a base, a vehicle, or a mobile base, and on top of it, you will have multiple uh, arms. Uh, right. So now that we have covered some topics, now we move on to few more other uh, extra topics. So now we move on to legged locomotion. Some brief overview of legged locomotion and how it is different to wheeled locomotion, which is something we were studying for the entirety of this course. So legged locomotion can be of you know multiple kinds. So over here in the first figure, it basically depicts a like you know dog like robot which has four legs or four limbs. Just like how a mammal or a dog would basically move. And on the second figure, you have something called a bipedal robot, which has two legs. Very similar to how human beings move. And on the third figure, you have you can call this to be an hexapod, which will have 6 legs, or if it has 8 legs, you can call it as an octopod. And this would mimic how an insect would locomote. And like they have a very peculiar view of locomotion in case of an insect, right? Because their diagonal legs are always synchronized, depending on the speed at which they are moving. So the key defining characteristics of legged robots are in legged robots are types of mobile robot which uses articulated limbs such as leg mechanisms to provide locomotion. So like just like how uh, we have legs in a human body, in a legged robot they have legs, and each of these there are multiple members actually, and each of these members. So like I'll label this as probably member one, and this to be member two, and each of these members are essentially connected using joints, right? So I'll call this joint as the hip joint. So hip joint basically connects the limb, or the leg to the main body, and I'll call this joint to be the knee joint. And the third joint, I could call this to be the ankle joint, right? And each joint will be, actuated using motors. So like you will be placing some motors in the axes of, attached to the axes of the hip, knee, and the ankle joint, right? And the motion of that motors would impart motion to the joints of the knee. The second feature is they are more versatile than wheeled robots and can easily traverse many different terrains. Though these advantages require increased complexity and power consumption, right? So in case of a wheel mobile robot, you only have a single motor, to rotate the wheel. But in case of a leg, as you can see, you have at least 3 motors for each leg. And if you have 4 legs, you will have at least 3 multiplied 4, which is 12 motors or 12 inputs. So, that essentially increases the power consumption by quite a big margin. And, there are also additional challenges because, legs are inherently unstable. And, if you apply some force, on these sort of robots, there is a very high chance that they may topple over. No such threats for a mobile robot, but in case of a legs, you have to deal with the stability issue. But there are advantages, right? If your terrain is actually very rough or very non-smooth, or if it has undulations, legs can move through this irregular environment much more easily than a wheeled mobile robot. So the third point is they often imitate legged animals such as humans or insects in an example of biomimicry. So like what we are trying to do is we are trying to replicate how organisms move using their legs. So, and we know, there are several solutions in the animal world uh, where they use legs in a different manner, right? Humans only walk on 2 legs. Insects walk on 6 or more legs. Most mammals actually walk on 4 legs, and the way at which they are actually walking is, it's very different. All right, and yeah, let's see the advantages and disadvantages of legged robots. So in legged robots, they offer high mobility, right? So like if there is if there are a lot of steps or a lot of very high obstacles, mobile robot won't be able to overcome those steps, but a very well calibrated legged robot can easily tackle or easily face such obstacles. and less effect on uneven grounds. They are much more efficient, or much more uh, uh, you know they can easily tackle uneven ground, essentially. Less damage on the environment. So this is actually a very subtle point, right? So if you are uh, probably deploying a wheeled robot and a legged robot on an environment, maybe on a very sensitive environment, the wheel robot may probably leave wheel tracks, right? Especially if it is heavy, it may leave some sort of tracks, wheel tracks, as it moves along the environment. So it leaves some sort of a footprint on the environment. Whereas in case of a legged robot, it'll only have a very minimal footprint. That too, depending on the point of contact of the legs. So in that regard, the wheeled robot essentially flattens everything as it goes, but a legged robot, will have a very minimal footprint on the environment. And legged robot will also have higher velocities on uneven ground. If you can stabilize it adequately, it can also move it in a very high pace. And legged locomotion, at least for animals, you know, they are better for energy consumption, right? Like if you want to move in a very fast way, or if you want to move very fast, very high, uh, legs are actually the best possible way to move in our real world. All right, then legged robots are designed for locomotion on rough terrain and require control of leg actuators to maintain balance. Right. So like they have this inherent stability issue, and you have to control all the motors of all the joints so that that stability will be maintained. And you will also need some associated sensors, and sensors are needed to determine the food placement and planning algorithms to determine direction and speed of movement. Right. So a lot of factors are there to be taken care of as the mobile robot moves. And another thing that one would often, find itself when we are dealing with the legged robot is the term called gait, GAIT. So the definition is that the periodic contact of legs of the ground, legs of the robot with the ground is called gait of the walker. Right. So as you know, the leg would execute some periodic motion, right? It'll execute some back and forth motion. So at one instant it'll be like this. These are the joints, and at some other instance it could be very straight, and some other instance it could be something like this, moving backward like this, three joints. So like we would execute these motions periodically, and this periodic motion of the leg, in the legged robot community we call that periodic motion as gait of that leg or of that walker. And the final point is, in order to maintain locomotion, the center of gravity of the walker must be supported either statically or dynamically. So, in case of a static equilibrium, like when the robot is stationary, the key important point is that, if the robot had four legs, right? Maybe this is the point of contact of the first leg. This is the point of contact of the second leg, the point of contact of the third leg, and the point of contact of the fourth leg. You could basically draw a polygon, that essentially encloses or essentially connects all the four points of contact of a leg. And the static stability essentially requires the center of gravity of that entire robot to be within this polygon, within this closed polygon, right? So like you can also think about a chair or a table, right? have a brief sketch of a table like this with 4 legs, right? And you could consider these points to be the point of contact of the 4 legs with the ground. And if I draw a polygon connecting all these 4 points, the center of gravity of the table should be within this polygon, right? And if the center of gravity is outside this polygon, maybe if you are keeping a very large weight over here, and if the center of gravity is shifting, outside, outside this polygon, so in that regard, the table would topple over. The table is no longer stable. So the same thing also ensures for the static equilibrium of legged robots. The center of gravity should be within the polygon of that point of contact of each of these legs. And you have to balance this statically as well as dynamically. Like when the robot is at rest, you call it as a static equilibrium. And when the robot is in motion, there is you also have to take into account the weight shift, right? So if the robot is moving forward, the weight will be shifted to the back. And if the robot is decelerating, or if it is coming to a stop, the weight will be shifted to the front. So the stability will have to be accommodated, or you have to shift the legs so that the stability will be accommodated. Right. That's about legged robots. And then we talk some more regarding uh, we have a general discussion about healthcare robots and how robotics are used in healthcare, and how they are classified. So the key differences or the key as areas where we deploy robots in healthcare are these 4 categories. The first category is surgical robots, where we use robotic systems for assisting a surgeon for conducting some surgeries. And the second application is exoskeletons, right? Maybe if a person is if a person has lost some uh, ability of a limb for it to properly function, you can actually attach an exoskeleton to that limb, which would assist that limb to perform adequately, or to lift some weight. And another aspect is rehabilitation, right? For example, in if a if a if a person is suffering from strokes, symptoms of stroke, he may be paralyzed in some part of his body. Or if a person is actually recovering from a very serious accident, or if a person is recovering from a severe very serious surgery, it may take some time for that person to completely regain the functionality of his limbs. And it requires a lot of physiotherapy, right? And as you know, physiotherapy would always rely on the services of a physiotherapist. So in rehabilitative robots, a robotic system would replace a physiotherapist, so that required strengthening or required training motion of the limbs will be performed, or will be the assistance for that training action, or that muscle strengthening action, would be assisted with the help of a rehabilitation robot. And the fourth class is actually care and hospital robots. Robots uh, which would serve as a companion, not necessarily performing any task, but probably as a companion for patients as well as doctors, as an assistant. And there are a lot of advantages of medical robots. They have excellent geometric accuracy. So, like for example, this actually, you know, uh, helps a surgeon to perform very intricate surgical operations. So, like for example, if some sort of a stitching is required, in micron scale or micrometer scale, human arms cannot, do an operation or a task with that much accuracy, right? But a robot essentially can do that. A robot operating on a micrometer level accuracy essentially can do such task. And what essentially we do is that a surgeon will be typically working on a master robot, in a scale that is comfortable for him. He would be operating on a centimeter level of scale, and a slave robot will essentially scale down, the movements of a surgeon into that required micrometer level of accuracy, and the slave robot would essentially carry out that actual operation, within that patient. So yeah, we can actually essentially use the excellent geometric accuracy of robots to perform some intricate applications, and they are untiring and stable, right? They are not really burdened by their by the continuous tasks. They are immune to ionizing radiations, such as X-rays and all those, so they can be deployed in rooms to assist patients uh, uh, where uh, where they are subjected to excessive radiations. Uh, then for the fourth point is they can be designated to operate at many different scales of motion and payload. Like just like we have discussed in the first point, they can be recalibrated to operate at very minute scales. And the fifth point is they have the ability to integrate multiple sources of numerical as well as sensor data. Their motion would rely completely on their numerical models, their mathematical models, and whatever they observe from the sensor data. All right, so there are a few limitations of healthcare robots, which are poor judgment. Like they may not be able to, make their own decisions based on what they actually see, and they are hard to adapt to new situations. So in most cases, they are typically designed to perform one specific task. They have very limited dexterity. They have limited hand-eye coordination. They have limited haptic sensing. So like haptic sensing is something, uh, we can define haptic sensing using the following example. A surgeon can essentially touch and feel, how each of these organs would feel like. So in a lot of applications, the surgeon can do a very accurate diagnosis based on his sense of touch. Whether or not maybe a tumor is malignant or not, and whether it is cancerous or not. He can fully have a very good diagnosis based on his tactile feedback or his haptic feedback. But that sort of a feedback is not possible to obtain, from a robotic system, right? A surgeon would not be able to, get that sort of tactile feedback if he's using, if he's using a robotic interface. And the next point is limited ability to integrate and interpret complex informations. That is also one more drawback. Uh, and before moving on to the questions, we would also like to discuss a few control paradigms. Control paradigms which are relevant for surgical robots or healthcare robots. And the first approach is you could actually employ surgical robots which are pre-programmed or semi-autonomous, right? So in this case, the desired behavior of a robot's tool is specified by the surgeon, usually based on medical images. So based on the medical images, the surgeon can actually pre-program the tool's motion. Right? If a robot has to do some surgical operation, the surgeon can actually pre-program the robot for the next procedure or for the upcoming procedure, and the computer essentially fills in the details and obtain surgeon's concurrence before the robot is moved. So the surgeon would be providing, the inputs or the motions at some discrete points, and the computer program would essentially fills all the intermediate points, using some sort of interpolation. And before the tool is moved, the computer would see the permission or the confirmation from the surgeon, before the robot is executing each of this motion. So it's not fully autonomous, it's semi-autonomous. Some of the data is actually filled in by the computer, but before the computer executes some motion, or before the server executes some motion, it will have to obtain the concurrence or the confirmation from the surgeon itself. So in that regard, it's not fully autonomous, it's semi-autonomous. And the second aspect is teleoperator control, where the surgeon specifies the desired motion directly through a separate human interface device, and the robot moves immediately. So, you have a surgical table over here, and you have, a slave robot, which would operate at the surgery table, and at some other location, maybe in a control booth, or or a workstation, you have a master robot. This would be operated by the surgeon, right? So so the surgeon would basically give, or he would actually operate on a joystick, or his fingers would be mapped. The movement of the fingers of the surgeon would be read by this master robot, and this master robot would communicate, the movements of the surgeon's finger to the slave robot, and the slave robot will appropriately scale the motion of the surgeon uh, into the surgical table. So, like, if the surgeon is actually moving, if the motion of the surgeon's arm is of centimeter resolution, and the surgery requires micrometer precision, the slave robot will scale down, the motion from the centimeter scale to the micrometer scale. All right. And the next point is hands-on compliant control. Here, the surgeon grasps the surgical tool held by the tool held by the robot, or a control handle on the robot's end effector, right? So the force sensor senses the direction that the surgeon wishes to move the tool, and the computer moves the robot to comply. So in a lot of applications, you will have, the surgeon would be required to use multiple tools, uh, one after the other. So these tools will be held together using a common tool holder, which would be very heavy, which would be quite heavy for a surgeon to move within that surgical table. So in case of a hands-on compliant control, the surgeon would only effort a very moderate effort, and using the force sensors, the controller would understand which direction the surgeon would want the robot to move, or the surgeon would want the tool holder to move, and the robot would assist the would impart some assistive motion so that the tool holder can be appropriately placed. So once the tool holder is placed at the required location, the surgeon can actually essentially use that tool using its own hands. And if it is too heavy, the robot would, using that four sensors, the robot would, would execute the requisite motion, in the direction where the surgeon essentially wants the robot to move. So those are the three control paradigms which would be employed in a surgical robot. Now let's solve some sample problems. This would only require the background on what we have discussed so far. So again, these are descriptive. There won't be any numerical problems which we were solving up to the previous week. So let's solve, some sample problems. These can be solved without much discussions. So the first question is, in one of these control schemes, the surgeon specifies the desired motion directly through a separate human interface, and the robot moves immediately. Right? So which control paradigm is this? If the surgeon specifies the control motion directly through a separate human interface, you can call them to be the master robot. Yeah, exactly. The correct answer is teleoperated robot. So I suppose we don't need any further discussion on that. Yeah. So again, this is we have discussed this so far. So I hope we don't have to go through this again. And the answer is indeed a teleoperated robot. So going to question 2, the robot in which the wheels mounted at the end of the legs is called dash. These wheels can be active or passive to provide motions, to provide more options for terrain-specific mobility. Right? So, you have to select an option from the following multiple choices where, you have, it is said that the robot has legs, and, at the end of the legs, you have wheels. So what are these called? So, this is actually a leg. And just like how you expect a leg, this is the hip joint, this is the knee joint, and here you have an ankle joint. And at the end, you also have a wheel, right? So this can essentially switch between wheeled motion or a legged motion. And no, this is not a legged robot. This is actually uh, an articulated legs action. Robots in which wheels are mounted at the end of the legs. Right? If you have we probably have discussed in the first week, if we have sorry, it's articulated wheeled robots. Right? Because if this robot encounters a very smooth surface, its legs would remain locked, and it can actually move using these wheels at the end, right? And when it encounters some obstacles, these wheels will get locked, and it can actually use its legs to climb over the obstacles. So like it essentially combines the principles of a wheeled robot as well as a legged robot, right? So if you have a leg, and at the tip of the leg you have wheels, you call these to be articulated wheel robot, right? So it's actually wheeled plus leg legged locomotion. Yeah, so let me know if more explanation is required. Otherwise, the correct answer is articulated like robots. Yeah, so I hope this image is clear. These are a few examples. These are typically legs, and at the end of the legs, you have wheels. And here also, these robots have legs, but when the surface is smooth, the robot will kneel down, right? Because there are wheels at the knees and at the ankle. So like the robot will, slide in a kneel down position because there are wheels at the knees and at the toes. All right. So the correct answer is articulated wheel robots. And moving on to question 3, Dash is capable of navigating an uncontrolled environment without the need of a physical or electromechanical guidance device. It's capable of navigating in an uncontrolled environment, so it makes its own decision. Yeah, the correct answer is indeed AMR, autonomous mobile robot. So that is indeed the correct option. Moving on to question 4, the full form of AGV is, again, I suppose it's also a straightforward, easy question. The correct answer is autonomous, automated guided vehicle. Yes, that is indeed the correct answer. And moving on to question 5, uh, a dash is a robot that is intended to operate with dexterity in a workspace larger than of a fixed base manipulator. So a fixed base manipulator will have a limited workspace, but something out of this following option will have, you know, uh, in a larger workspace than a fixed base manipulator. So I automated guided vehicle. So in case of an automated guided vehicle, it's just a vehicle. It cannot perform any task, right? A fixed base manipulator can perform some task. It can it the notion of dexterity, will only come when we talk about a manipulator, right? Because only a manipulator can, you know, uh, perform some task which require some dexterity. Because I have explained what dexterity means earlier. When a point can be reached with all possible orientations, we call that dexterity. But an automated guided vehicle, that it is just a vehicle. It does not have any. It does not have any uh, manipulation capabilities. Only a manipulator has, capability to perform some task. So a fixed based manipulator will have, limited workspace. But in case of but in case of, if you mount a fixed base manipulator on top of a mobile robot, you have essentially unlimited workspace, right? So if I call this a vehicle, yeah, and if I mount a manipulator, a typical robot manipulator on top of this, on top of this vehicle, the workspace of this manipulator is essentially much larger than a fixed base manipulator, right? So in that regard, the correct answer is, vehicle manipulator system, which is a vehicle that is mounted on top of a manipulator. So just a mobile base, don't do any task. A mobile base is just a mobile base. You can probably do some surveillance task. You can observe the surroundings, but a vehicle on its own, it's not capable of performing any task on its own. You have to attach a manipulator on top of it. So a mobile robot, again, it's just a vehicle. A wheeled mobile robot is also, just a base. Legged robot is also, just a vehicle. You can consider it just to be a vehicle. Aerial robot is also just a vehicle. Underwater robot is also just a vehicle. But a vehicle manipulator system, you are actually mounting a manipulator on top of a vehicle. You can mount it on top of a wheel mobile robot. You can mount manipulator on top of an underwater robot. So on and so forth. So I hope that is clear because this term dexterity is often associated with manipulators. All right. So moving on to the next question. Dash allows the robot to have periods of operational independence subsequent to coordinating their tasks or roles. So, like again, we have actually seen, a classification of, uh, how how we can classify a multi-robot system, based on their level of coordination, and based on the kind of members of that constituent system. So here as well, you know, uh, I think we have seen this collective swarm systems, and the other classification was, intentionally cooperative systems. And under here, if you can recall, we discussed two such cases: weakly uh, coordinated and a strongly coordinated. Yeah, so yeah, exactly. The answer you gave is indeed right. Weakly cooperative systems. So just as the name specifies, their level of coordination is actually very weak, depending on the situation or depending on the task. And weak cooperation means in most of the time, they are, you know, independent on their own. So that is exactly what the question says. They have operational independence, and when required, they can perform some task, cooperating with other roles. So the answer is indeed weakly cooperative solutions. So again, just the summary what we have covered so far. These are the screenshot taken from the lectures, and the answer is indeed weakly cooperative solutions. And moving on to question 7, we haven't discussed this in the summary, but again, this is a fairly straightforward question. A fixed wing aerial vehicle require runway. They may stall and need aerodynamic designs. Is it true or false? Like we have seen aerial robots, which has fixed wings, like aeroplanes. Aerial robots can have a single rotor, like a helicopter. An aerial robot, can have multiple robots, just like a drone, which has multiple rotors like this. So I label this as rotors. Right. So in case of multi-rotor systems or single rotor systems, they can vertically lift off, right? They don't need any runway, right? They can take off and land uh, vertically without any real requirement of a runway. But in case of a fixed wing aerial vehicles, like a drone, very similar to an aeroplane, they may need a runway for taking off and landing. And there is something called stall. I hope we know what a stall is. If the angle of attack of the wind is higher than a threshold, that wing essentially fails to produce any lift. And that phenomenon, what we call it as a stall phenomenon. And once that wing is no longer capable of producing any lift, the aircraft will fall down. So the question says fixed wing aerial vehicles require runway. So that is essentially true, right? Because fixed wing aircraft, they need sufficient airspeed to maintain or to generate lift, and to maintain to achieve that airspeed, you require a runway, and they may stall and need aerodynamic designs. That's also true. So I hope without much clash, we can all agree the correct answer being true. And again, this is just a snippet taken from the lecture, regarding different types of UAVs, the one with fixed wing, and UAVs like a helicopter, which is capable of vertical takeoff and landing, and things with multiple rotors, which is also capable of multiple, which is also capable of vertical takeoff and landing. And recent advances on bio-inspired UAVs, which has flappable wings, just like how a bird would fly, or an insect would fly. Yeah, so that's the correct answer. And moving on to question 8. In the one of the following approaches, each robot oversees the action of a relatively small group of other robots. Each of which in turn oversees yet another group of robots, so on and so forth, down to the lowest robot, which simply execute its part. So again, this is a straightforward definition to one of the following control architectures, right? Like we have essentially seen exactly. This is a straightforward definition for this hierarchical architecture. We can also call it similar to how the military line of command is followed. Again, we can all agree to that fact. The answer is indeed hierarchical architecture. Yeah, the answer is indeed hierarchical architecture. And moving on to question 9, rehabilitation robotics has been defined a special branch of robotics which focuses on machines that can be used to help people recover from severe physical trauma or assist them in activities of daily living. Again, that is indeed true, right? Essentially, a rehabilitation robot essentially, uh, performs a task, or performs or assumes the role of a physiotherapist to help people, regain their limb motion from physical trauma, or trauma associated with strokes. So that is indeed true. Moving on to question 10. In one of the following options, a large number of homogeneous robots execute their own task with only minimal need of knowledge about other robot team members. So here, the keyword to look out for is homogeneous robot. So like in one of the multi-robotic systems, we actually emphasis on the fact that multi-robotic systems, homogeneous robots are employed in that specific system. Yeah, so the answer is indeed collective swarm. That is indeed the correct answer. And moving on to question 11, in one of the following architecture, the coordinates an entire team of multiple robots from a single point of control, and is vulnerable to a single point of failure. That is centralized. It is indeed the correct answer. Again, I think we may have three more questions, I believe. I think this is what we have seen so far, right? Okay, this is a different question. In this case, this is the most common approach for multi-robot systems and typically require robot to take action based on the knowledge local to their situation. So like it's not really does not really bother about what other robots are doing. Their control is only local to their own situation. This architecture is also highly robust to failure since no robot is responsible for the control of any other robot. It's not really hybrid though, right? In hybrid, we would also talk about, you know, uh, ease of passing the information to all the robots. Here the control is exclusively local to that robot itself, right? So control is exclusively local, and in case of a failure, no other robot is responsible. So in this regard, this is actually decentralized. I know it can be frustrating because in case of a hybrid control, there were also a few more points. It's similar to how easily the flow of command can be passed from a central server to all the robots. That is centralized, the option. And question 13, it's again a true or false question. AGVs are capable of navigating an uncontrolled environment without the need of physical or electromechanical guidance systems. So are AGVs capable of navigating an uncontrolled environment, or is it applicable for AMRs? It's applicable for AMRs, indeed. So the answer is indeed false. So let me have a quick overview of how many questions are remaining. I think all the questions are more or less similar. Maybe we can solve maybe this one more problem, and all the other problems I can, upload in the Google form. Is that fine, or should we go with all the questions, all the 17 questions? I think we still have time. Should I go with the questions, or should I go, or should I stop with question 14? Should I stop with question 14? Because all the questions I feel it is repetitive and it's very similar to what we have covered so far. Okay, we can stop with question 14. So in this case, select the wrong statements regarding AMRs and AGVs. So we could have multiple correct answers. So the question says you have to select the wrong statements. So like we'll go one by one. We'll go one by one with each of these statements. The first statement is AGV requires fixed routes. That we can all agree that this is a true statement. AGVs or automated guided vehicles, they require fixed routes. Okay, the second option says AGVs have high flexibility. That is obviously false, because every time you need a new task, you have to create a new path. You have to recalibrate the AGV. The markers for laying out the path, it will have to be laid again, for a different task. So AGVs are not really as flexible as an AMR. The third option is AMR are more suited for traditional business than agile business. That is also false, right? In case of an agile business, the task would be changing at a very rapid pace. And for an AMR, it is very easy to recalibrate than in AGV, because in an AGV, you have to, recalibrate the path. Everything will have to be recalibrated. So, yeah, 2, 3, 4 are all False. That is your answer. AGVs are also not cost effective, when you consider the flexibility into account. And the final option is AMRs are capable of navigating in an uncontrolled environment. That is actually true. So the false or the wrong statements are actually options 2, 3, and 4. So that should be the answer for this question, 2, 3, and 4. All right. And all the remaining questions are, I feel, they are going to be repetitive, and it essentially covers what we have solved so far. All right. So with this, I would like to end this session. So, this will be our last session for this course. We won't be having any more live discussions on this course. So if you are taking the certificate exam, I wish you all the best. Right. So if you have any more questions, let me know. If you have any doubts regarding any of the topics, let me know. Otherwise, maybe we can wrap up this session. Uh, okay, no more doubts. Thank you. So yeah, with that, I formally sign out. From the weekly discussions. Thank you for joining. You have been the sole participant of this session, and unless I'm very much mistaken, you have also participated in previous sessions as well. So I appreciate that for your patience. I can imagine how boring these sessions are, but thank you for your persistence. Yeah, with that I am stopping this session. Yeah, thank you very much. Thank you.